Simply makes no sense to me. Rather than that, when you are confronted with this type of definitions and axiomatic structures, what you need to do is understand what it means. This is just a language, it conveys a meaning, and what is scary, because we are not used to use it, is this mathematical structure, mathematical language. This is what is overwhelming. It feels overwhelming because we are not used to use it. So rather than taking that definition by heart and learning, let's discuss what it means, and intuitively, graphically, and then we see what it says, right? So, concavity, convexity, those are properties that are not global. They don't necessarily apply all over. They can apply just in an interval. We may have an interval AB, and in that particular region, a function can be concave or convex, whatever. So, let's discuss what this definition says intuitively. And I'm going to take that definition later to make my point. I'm not interested in concavity itself. I'm interested in concavity or in the Jensen's inequality because that characterizes the way of thinking of the representative label for us, who is a risk-averse guy. So what that definition says intuitively, how can we characterize concavity? So we have a function, we have a plane, that's going to be for us. I'm going to stay away from utility. I just have x here, and I'm going to have fx in this axis, okay? And then I'm going to go for a concave function, something like that. Plot it any way you want, but I want this type of curvature. It needs not to be in the whole range. We define concavity or convexity in a given range. So I'm going to take something like this point, this interval, A, and over here, for instance, B. And I want to characterize things in A and B. This is the interval AB that the definition says. This is A, so this is FA. This is B, so this is FB. Now, we characterize concavity or convexity by saying for any lambda, so I'm going to give you a value, lambda, in the O1 area. And I'm going to create a point, X bar, that weights alpha, that weights, A, and B like this. So this is a weighted sum. And because you are taking lambda in O1, it's like a probability. This is a weighted sum. By taking this any lambda that you want, what we are constructing is a middle point. If I take lambda 1, I'm taking A. If I take lambda 0, I'm taking B. Any midpoint between 0 and 1 takes me somewhere in the middle. You see the what we are constructing? You consider an interval, AB, take any point. All right, any. So I'm going to go, I don't know, from here. That's going to be my middle point. I construct this, I take one, right? It can be any, but I'm going to take that one. So this point here, this is the function of my midpoint. All right, A, FA, FB. Now I'm going to trace out a line connecting FA and FB. This is called a chord. Linking A and B. I'm taking my midpoint up to here. I'm finding this point here. This point here is lambda FA plus 1 minus lambda FB. Is the middle point between FA and FB, given your choice of lambda. So I'm going to call this guy F bar. So what is the characteristic of concavity? The characteristic of concavity is that all these points in which we may evaluate the function at the middle point are above the points that we trace, that we can link, right, when constructing the average, or any lambda you like, right? You pick up some lambda value here, that guy is going to be above the points that will be constructed linearly. So this is what the definition is telling me. You want to characterize concavity. Concavity makes the function evaluated at the midpoint above the average of the function evaluated in the point. The function of a midpoint is greater than the mean value of the function in a point. It's not linear. It's not the same like, say, the function of the average is the average of the function. That holds for linearity. When the function of the midpoint is about the mean value of the function, that's concavity. When the function of the midpoint is below the mean value of the function, you have convexity. That's concavity. Concavity, convexity would be the neuro, would be below. So concavity is like that. Concave, like a cave. Convexity is like this. And mathematically, it's characterized in this particular way. Okay? It's understood. So the definition sounds super ugly, but what it means graphically is just like that. So we have these definitions. Those are mathematical definitions. We say that when the function evaluated at a midpoint is extremely greater than the mean value of the function, so if you like, I'm going to put it right. The function evaluated at the midpoint will be like a alpha a plus 1 minus alpha b. So that's the function evaluated at a midpoint. When this is extremely greater than alpha fa plus 1 minus alpha fb, like I said, it's repeatable, right? F of the midpoint is greater than the average of F. This is called strict concavity. If you replace this inequality by greater than or equality, so you allow points to be equal, not just greater, but also greater than or equal to, then we don't have a strict concavity, we have just concavity. So an example of a strict concavity would be, for instance, the natural logarithm of x. A strict concavity is a function like a natural logarithm. All the points are above the midpoints. But if you allow the equal sign, then an example of concavity, for instance, is the line. A line is concave because it matches the definition of concavity when you permit that the mean value, the function evaluated at the mean value, equals the average of the function. If we reverse the sign, inequality, so f of lambda a plus 1 minus lambda b is extremely smaller than lambda fa plus 1 minus lambda fb, then this is called strict convexity. And you have reversed the scenario. Right now, you have something like this. And that's a strict convexity. And if you replace the smaller than by a smaller than or equal, then you don't have a strict convexity, but just convexity. So convexity, once again, will be the line. A line, according to the mathematical definition, a line is both concave and convex, both at the same time, because we are characterizing properties and both properties are matched. So a line is both convex and concave, but it's not straight concave nor straight convex. All right? So, given these definitions, we can characterize this aversion. We're gonna discuss that and say why a guy that has this aversion is someone that can be characterized in these terms. I'm gonna pick up this because the analysis is going to be very similar, so I'm gonna take this one. Okay, can I clean here?
No.
Let me use this one. Alright. So this is what we are doing. I'm going to consider an individual. This individual has an initial wealth omega 0. That much money. This guy has an utility function that is evaluated at that point. In the initial state, right? That's the initial state. This guy has this wealth, this is certain, and then he's so happy in terms of a given utility function. That utility function is a proper utility function, so the first derivative is going to be positive, and we can consider three types of preferences. I'm going to here consider the most significant one, which is the risk adverse, the standard utility function, increasing but marginally decreasing, like a natural logarithm. And to that guy, we are going to show you. That's the initial wealth of that guy. We are going to force him to play a game in which his wealth omega 0 is going to be shot by a fair game. If it rains, he's going to lose C. If things go right, he's going to make C. And the probability is going to be a half, such that the expected value of this epsilon is 0, the condition of the fair game, and the variance of this epsilon is sigma squared. I want to see what it's going to do and how it's going to keep, how we will feel about the idea of being shocked in these terms, in terms of expected utility. When I have in the initial conditions, we talk about utility. If I shock the wealth, his final wealth will be the initial wealth plus the result of epsilon, so minus C with probability a half, or plus C with probability a half. And because this is random, his total wealth after playing the game is going to be random as well. So he will evaluate his new state using the expected utility of wealth. Utility at this point, but if you force me to play in a random game, expected utility. So I want to see how these things emerge and why he will dislike this game. So this is wealth, utility in this axis. I'm gonna make a function like that. Feel free to put something in these terms. It will not look exactly like mine, but that's fine. It will be your utility function. And because every individual has a utility function, that's fine. And I'm gonna take this area here. That's gonna be the initial wealth. This is the utility of omega 0. This is the initial state. He's happy, given this head as well. This is this happy. You know that the utility, the units of the utility doesn't matter. Utility is not meant to tell me utility has 1,000 units. Utility is just a device to make cardinal comparisons. If you are better, your utility will be greater than this level, and that will make you happier. And if you are worse, when your utility decreases, and that will make you feel sad, right? So this wealth is going to be short. We are putting the good side of the story. When you get plus C, and you get all this much in wealth, in the wealth axis, and we are gonna be fair, so the same amount is lost if things go wrong. This happens with probability P, this happens with probability 1 minus 2. And that's why it feels fair. Same amount if you gain, same amount if you lose, right? Now, if things go right, your utility will increase up to this much. So this is the utility of the original wealth plus C. When things go right, you will go up to here, more wealth, more utility, you will be happier with that. But if things go wrong, then you reach this null point, and then this is the utility evaluated as the new level of wealth that has decreased, and hence, so decrease your level of utility. At this point, it should be clear graphically why this guy will dislike this game. Can you see? Can you tell me?
The benefit of winning is way less than the benefit of losing. So he much rather be paid to participate to offset that difference.
Like Isaac said, the game is fair in the wealth dimension. But how it feels, this is not where you make decisions. You make decisions in this scale. How it feels is when you have something to gain, you gain all this utility. And that of course makes you happy. This much is what you will experience if things go right. But if things go wrong, you lose all this. So it is fair in the wealth dimension, but the nonlinearity, the concavity of the utility function makes the drop in the utility bigger when you experience the negative side of the game than the increase in the utility function when you experience the good side. With the same probability, you have more to lose in terms of utility, not in terms of wealth. Wealth is fair, but in terms of utility, in terms of happiness, I have more to lose than I win. No individual having this function will accept playing this game because it feels unfair inside of in my subjective perception is unfair. It is fair on the world dimension, but it's that I don't make decisions on the world dimension. I make my decisions in terms of utility, and what I drop or I lose is much more than what I have to pay. So, end of the story. At this point, this is enough to claim someone having this utility function, which is not meant to capture this aversion. This aversion is a side consequence of having this nonlinear function. The consequence of being satiated, the experience that makes us feel satiated, right? After the first beer is okay, but after 5 beers, I don't want any more beer. That thing is the same thing that makes us feel this aversion. This aversion is a kind of side effect. If I have this utility function, I will dislike this fair game. I have more to lose than I have to win. Let's elaborate a little bit more on this, okay? The chord that we traced out before. I start from this point to this point. This point here is my initial wealth. But that point is going to represent as well, this point is going to be also, this value is also the expected value of my initial wealth plus the result of the game. Because this clearly is going to be omega 0. The expected value of a constant is omega 0. plus the expected value of the shock is 0, around on average, I will be here. Like we said before, I know that after the game, I'm gonna be either here or here. It's going to be either here or here. But on average, if I play this game 1,000 of times, sometimes up, sometimes down, on average, my wealth stays at the same level. Sometimes I win, sometimes I lose, on average, I remain at the same level. So if I take this point as the input for the expected utility function, we are gonna go all the way up to here. And this point here is going to be the expected value of the utility evaluated when I play the game. When I don't play the game, I go up to here. If I play the game, the axis is the same because I stay at the same point, but now in terms of expected value, I end up at this point. Of course, what happens is, that was my initial level. Now, if I have more to lose than I win, than I make, than I earn in the utility function, then what I expect is a drop in the expected utility. I dislike this game because my utility is at this point, because I have more to lose than I make. My expected utility is smaller than I have. The new level of expected utility that I'm gonna find is here. So I lose all this. In terms of change in the utility function, when I replace the utility of a certain wealth by the expected utility of when it comes with the game, I reduce and in a lower point. So that makes the point clear. You will not willing to pay, you will not be willing to play this game. And that gives me 2 points, 2 new points to understand. If I go here, I see this point, right? And that takes me all the way down here. So let me use a different color. I am going all the way down to this amount. So let's call it omega star. Omega star is a point for which the utility evaluated at omega star is the same as the expected utility when evaluated at my omega star, my initial wealth plus the outcome from the fair game. In other words, if you force me, because the word is force me, I will never, as a disadvantaged individual, will never take this game voluntarily. If you force me to take this game, I will experience a reduction in utility. And that's equivalent to take an amount for sure. This omega star is the certainty equivalent. I experience a reduction in utility, and then I will say you, because this is negative for me, I will say, I'm okay if you take out all this wealth, certain, or if you force me to play the fair game. In other words, playing a fair game feels like losing a certain amount of money. The reduction in the money that we are losing, all this, is the maximum amount that we will be willing to pay in order to avoid playing this game. I'm willing to pay for avoiding this game, because for me it looks like a losing money. But of course, I cannot pay more than that amount that I expected to lose. This is the risk premium.
Can you explain one more time the wealth asterisk?
That's the certainty
Yeah,
equivalent.
can you explain that concept again?
So, you see that, right? When you play the game, this is gonna be your expected wealth. Your initial plus 0, so you stay here. But when you evaluate the utility, You cannot go up to here because that was the certain value, the omega. Now it's omega plus error, so you don't go up there, you go up to here, just like we did there. You evaluate at the middle point, you evaluate at expectation. If you want to evaluate at this point understood as an expectation, then you don't reach that point because of the concavity. You will reach this point because of the very definition of concavity.
And
then we trace out. All right. So this is the new level of utility you are going to find. You are forced to play this game.
yeah, that's with the level of uncertainty, right?
Then, for this level of utility, at this point up here, we found a new level, which is omega star. So having omega star has the same utility as having omega 0 and being forced to play the fair game. So this is the certainty equivalent of playing the game. In other words, what does it mean? If you give me two choices, you are going to have your initial wealth and you are forced to take the result of the fair game. Or I give you reduce your wealth right away up to omega star. You feel you will be indifferent. It's the same, it feels the same, that you remove me 100 euros or you force me to play this game. This stupid game that I don't want to play. I don't want it to play because it feels to me like a reduction in my original rate. Because you have the same level of utility, there is no risk here, this is the certainty equivalent. And again, that's why you don't want to play this game. Because it feels like you are losing for certain amount of money. And then we can construct another related concept, which is the risk premium. If playing this game feels like losing money, that difference is the maximum amount I will be willing to pay to avoid the game. In other words, imagine that I could pay an insurance, a fee to someone saying, I don't want that shot. And someone comes to me and tells me, Antonio, look, if you pay me A, you can avoid that risk. The question would be, how much A should be? And the answer is, I will not pay more than this level, because the reduction in my wealth is bigger at this point, then the utility is even smaller. Even though this is bad, paying more than this amount is worse. So the risk premium is the maximum amount that we will be willing to pay to avoid the first game. And now, think about it, it's a fair game. It's not like it's bad itself, it's zero expectation, but because we are risk adverse, it feels bad. It's understood, guys? Because there are three important concepts to understand here. First of all, risk aversion comes from concavity. Second thing, for a risk averse individual, the certainty equivalent goes below you, and because it goes below, it means loss. That means that you are willing to pay to avoid risk. And hence, that's why we call risk aversion. You dislike it. You are willing to pay to avoid that risk. This is the formal justification of the insurance market. There are a market for insurance because people are risk averse. If people were not risk averse, no one will ever pay to avoid that risk. If people were risk neutral, we'll be perfectly okay. But because we are risk averse, we avoid those risks. Is that understood, guys?
Antonio, so the certainty equivalent is a wealth level that doesn't exist in the game because you're either.
But we can theoretically, it's a theoretical amount that we can identify at the theoretical level.
So it's the amount of wealth you feel you have, given how you feel when you play the game. But it's not a wealth level that I am. It's in reality out of my preferences or my feelings.
It depends on your preference. It is personal, it's specific
like
to
I
each
have that
person.
wealth.
That would be, might like I said, you don't like, it might like I said, let's play a game. Heads, you make 100,000 euros. But tails, you will have to pay me. You want to play this game? Most people will say no.
So
It might that it force you. So how much will be you willing to avoid this burden, this liability? So that reduction is the risk premium, And what is left after taking the risk premium is the certainty equivalent.
So paradoxically, if the individual is risk averse and he pays some risk premium, then he ends up with lower wealth.
But exactly.
So
This
he,
is
he
but
loses
that's the
the-
max. But this is the maximum. That's why this is the proof that you decide risk. In your world, it feels like I'm losing money right away. You decide losing money for certain. Playing a fair game implies the same feeling. So let's say that we are talking about the initial wealth, let's put it in 1 million. Alright? Let's shock this guy with 200,000. So the wealth of the guy is gonna go to 800 or 1.2 million. And the guy says, I don't want that. I don't want to lose 20% of my wealth, just one shot. Even if you give me the same probability of making that 20% extra. I don't want that. I don't want that. And the question will be, how much are you willing to pay to avoid this thing? And the guy says, let's say that the guy says 10,000. Then the risk premium will be 10,000, and the certainty equivalent will be 990,000. Is understood now?
Yeah.
You don't like it. The point is, you don't like it. And you don't like it because it feels like a losing money. So I can take advantage of that feeling to say, if you are gonna lose, you are somehow in your personal mind, you are losing money. So for instance, if I offer an insurance, say you are willing to pay up to 10,000, if I offer you an insurance for 2,000, you will be super glad to avoid the chance of losing 200 and making 200. And the paradoxical point is that this is a fair game. Initially, it's not a bad thing. It's not that you are doomed to lose money. No, 50% you lose, 50% you win. But the point is that in our personal perception, this is like a losing money for sure. In utility, it feels like losing. Why? Because we are more sensitive to losses than to gains. The problem is that because of this nonlinearity, our loss function is asymmetric. We are much more sensitive to losses than to gains. And because you are giving me the same size of loss and gain, I don't accept because it hits my feeling of loss. I'm sorry, I'm not symmetric. Making 100 is good, but losing 100 is much worse to me in my feeling, in the way I perceive life. So when confronted with 50-50, the same both scenarios, I dislike that. And to me, it feels like a loss. I dislike it because it feels as if I were losing money, for sure. So with this feeling, we can define these objects, the certainty equivalent and the risk premium. Pratt's risk premium. Let me emphasize this idea because this theory has evolved over the last 50 years, and that was the first definition. So there are two definitions of risk premium. This premium here, this risk premium, understood as the amount that you will be willing to pay to avoid this fair game. This is called, in order to make the difference, Pratt's risk premium. And that is expressed as measured in euros. That's how much money would you be willing to pay. The modern conception of risk premium, what we call nowadays just risk premium, is not expressed in dollars or in euros. It's expressed as a percentage, it's a rate of return. The nowadays conception of risk premium has evolved from the primitive, the first approach dimension, which is Pratt's risk premium, insurance premium, to return. How much return are you willing to give, or to how much you demand in order to be exposed to a risk? Okay? So the change moves from someone, it's like in early times we thought of someone taking insurance, now we think of someone going into the market to invest, knowing that he dislikes risk. He will invest if rewarded with something extra. Just because it's being exposed to risk is something that they dislike. Is understood the graphic rise and the interpretation, these concepts?
So just small clarification here. The W plus
Epsilon.
epsilon. That's basically the risk, like the wealth with a certainty, right?
This is this was certainty. This was the initial state, no risk. But down, when you put expectation, that introduces the result of uncertainty. It's not the same thing. And actually, this is the way in which we can also define this aversion. A risk averse individual, taking this omega, right? Omega, unexpected of omega plus epsilon. You prefer, which is also omega. You prefer this scenario to this scenario.
A certainty.
We see, right? Exactly. So we can define this aversion. We can define this aversion as someone that prefers 1 unit. Someone that prefers 1 unit certain over 1 euro expected. 1 euro certain. If you tell me I prefer 1 euro for sure, 100% chance, than 1 euro expected, you are risk averse. If for you both amounts feel the same, you are risk neutral. And if for you prefer the 1 euro expected, then you are risk over. And that comes from this representation. It's not the same, it is not, because the effect of uncertainty introduces a distortion. Introduces a distortion depending on your personal preferences. If you are risk averse, you will tell me I prefer the 1 euro 100% certain than 1 expected euro. And this is how most of us behave. Most of us, but not necessarily all of us. The representative agent in the stock markets, the representative agent making decisions, making economic decisions, is risk averse. So that's why we put too much emphasis on this idea of concavity. Okay? Understood, guys? We can elaborate a little bit more this idea of expected utility and say something about the preference and the risk premium. Let me do that and we finish today. Okay? I'd like to say something about this risk premium. Risk premium is one of the most important concepts in finance. It's, as I said, it's related to risk. Risk premium is the price of risk. So finance is about the price of risk. Like I said the first day in the presentation, people tend to simplify finance thinking, oh, it's just about, bringing money that is in the future. No. Finance, dealing is about this. Pricing things in uncertainty. And the purest operation will be pricing risk itself. What is the risk premium? What drives the risk premium? So in this characterization, we say something like the utility of your initial wealth minus the risk premium, and remember this was the certainty equivalent, right? That was what I call omega step. I have this kind of matching in the graph. If I evaluate the utility function at your original wealth minus the risk premium, this is the same as the expected utility of your original wealth plus the random shock that you find annoying. That's why you are going to be risk averse when you are going to wake up a positive risk premium. Now, we like to be able to say something more about the risk premium. Graphically, I'm saying things, but I would like to deep into this expression, mathematically. And I want to be able to deep without making strong assumptions. I'm going to use a tool that, for those of you that are seeing the Euler equations in at the start, with Antonio probably now is familiar, which is the Taylor expansion. Have you seen it already? Let me remind that, okay? I would like to say something about this structure, and I'm going to take advantage of what is called the Taylor expansion. My problem is that I want to say something about the risk premium. The risk premium is inside the function, and I want to pull that, I need to pull this out. It's inside, it's the argument of the utility. I know things about the utility is increasing, and it has a second derivative which is negative. But my problem is that in order to see something about the risk premium, I should be able to take that out, and it's inside of the function. So that's what the Taylor expansion tells me. The Taylor expansion tells me that a function f can be expanded at a point which is going to be, let's call it a, and a is arbitrary. You take any point a. So a function fx can be expanded around a. I'm going to use the approximation in an approximate way, meaning you should take values of x close to a. You want to do this thing, which is you evaluate the function at fa. And then you need to introduce correction. You need to introduce correction terms, because this, generally speaking, obviously cannot be fa. The correction terms depends on the derivatives. So a first order approximation takes the first derivative evaluated at a, and then, because we want to say things generally on x, you introduce this difference, x minus a. This is called the first order approximation. Taylor's first order approximation requires the function to have a first order derivative. Not every function has a first order derivative. Now, provided the existence of derivatives, we can get the approximation better and better. If this function f has a second derivative, then we can introduce a second order correction that refines the approximation, makes the approximation more accurate. So the second approximation would be a half of the second derivative evaluated at point a, x minus a squared. What is the idea, intuitively? I will have a function like this. I want to evaluate the function at this point. This is going to be my fa. This is a, this is fa, and the whole function is fx. The idea is that I can locally approximate the behavior of this function by using these derivatives. Overall, this is kind of function that looks like a polynomial, but in this region around a, this function looks really like a line. You notice that? I may approximate that in the neighborhood of a through a line. You want to go again, you need to introduce second derivatives and make perhaps this. And you record the first order derivative will be an approximation that looks like that. Over here is really poor approximation. Over here is really poor approximation. But in this neighborhood of a, the line kind of captures the behavior of a function that has a derivative. This is the idea of the Taylor approximation. I'm going to use this to expand those terms. I'm going to start from here. So I start to the right hand side. Utility, that's going to be my function. The utility evaluated at this point. So in order to make clear, to make more transparent what we're going to do, I'm going to take the point A, and I'm going to take A as omega 0. So the utility function, according to the Taylor expansion, will be the utility function evaluated at A. So I evaluate this function at omega 0. That's of course not enough, and then it's when we introduce those corrections. All right, first order correction. The derivative of the utility function, so marginal utility, evaluated at omega 0, times my argument, which is x will be here omega 0 plus epsilon. So x minus a, which is what the Taylor expansion is asking for when I do this expansion, will be omega plus epsilon minus omega, just epsilon. So epsilon is. And the second order derivative will be a half of the second order derivative of utility. So evaluating at this point, and then times x minus a, that we said is epsilon squared. So epsilon squared. And this is not exact, this is an important consideration. If you want this equal sign to hold, you keep going and consider an infinite number of derivative, second derivative, third derivative, fourth derivative, because we are truncating and the second order derivative, this equal sign is not correct. We say it's an approximate, it's a good approximation the closer you are at omega 0. So it's a very good approximation when epsilon is small. This is, of course, the price we need to pay for small values of epsilon. You have a very good approximation. For large values of epsilon, well, but my point here is that I will be able to extract things. Now, in this side of the equation, we have the utility, and we have the expectation of that utility, right? If that's true, then the expected value of this utility function is kind of, in an approximate way, equal to the expected value of all I have here. The expected value of the utility evaluated at omega 0, this is not random. That's the utility evaluated at omega, this is a non-random function. So this is the utility at omega 0, because it's not random. Plus marginal utility evaluated at omega. This part is non-random. So again, utility prime at omega 0 times the shock. That's random. And there's where we take the expectation. The expectation of epsilon is what? 0, because it's a fair game. So this term collapses. It's multiplying 0. This guy equals 0. And then we have a half non-random, utility non-random, omega 0 non-random, so that guy goes as a constant, times epsilon squared. The expectation of epsilon squared is what? Is sigma squared. The variance of epsilon. Because the variance of a random variable with 0 mean is just the expectation of the random variable squared. So this is what we have to the left side. And now we are going to finish to the right hand side. In the right hand side, we have the utility evaluated at omega minus risk premium. Again, I'm going to consider my x is going to be, my expanding point A is going to be omega 0. So x is going to be now omega minus risk premium, and x minus A is going to be omega 0 minus risk premium minus omega, omega cancels out, x minus A is minus risk premium. And I'm doing that absolutely knowing what I'm doing. The choices of the values are super intentional. I'm doing that to pull out the risk premium out of the expression. Just like this epsilon that was inside of the utility function appears outside, by doing the expansion in this particular way, I'm going to the point I like. I want risk premium out of the expression. So, using the integral expansion, this utility function would be, and now I repeat, all right, your function, utility, evaluated at the point that you are expanding around, which is omega 0. It's not enough, you introduce a first order approximation by considering the first order derivative. So we take the derivative and evaluate at the point we are expanding at, so omega 0. And then we multiply by x minus a, so the argument of the function, minus the expanding point, which we said is minus risk premium. So this is multiplied by minus the risk premium. This is the whole point of this analysis. Ending here. Now, the risk premium, which is what I want to say, this is my objective. I want to say something about that risk premium. This risk premium went out of the argument. And now I can make a linear thing. I can sort of manipulate the expressions algebraically because now this premium is popping up there. So 1, which is this side, equals this thing, which is 2. So this animal here looks equal to that animal here, right? If 1 equals 2, because this is where we started, then this stuff equals that stuff. So this term and this term are the same. They collapse, they are gone. This term is 0. And this term must equal what is left from this quality sign, which is this. I can go slowly. I don't want you guys to be lost here. But what I'm going to do is equal this expression to this expression. And because I have this utility evaluated at omega 0 in both, they are going to go up. I'm going to do it anyway, okay? I'm going to do that instead. So, quickly, from 1, I have that this thing plus this thing must be equal to what I have there down there, which is the utility omega 0 plus u prime omega 0 minus risk premium. And because we are working in terms of expansions, this equal sign now needs to be understood in terms of in an approximate way. You are approximating things to the left, you are approximating things to the right, so this sign it must be understood in terms of an approximately value. The point is, this guy and this guy cancel out because they are both at the same time. And we have here risk premium, so we can solve for risk premium in this expression. If this holds true, the risk premium must be equal to, in an approximate way, for small values of the epsilon random variable, in an approximate way, in a local neighborhood of omega 0, when this point is not very far away from there, this risk premium will take this expression. This is on the side, this is multiplied by u prime omega 0, that goes down, that negative sign pops up here. That negative sign is going to be there. We have a half, so we're going to have sigma squared half. Then the second derivative divided by this term, which is multiplying here. So this is u prime omega 0. So this is what the risk premium looks like. And I said that in a very general terms. The beauty of the analysis that we have done right now is that it builds on a very general set of assumptions. The only assumptions I make is that u prime exists and the second derivative exists. This is all I said. Then you will have a risk premium that has this shape. And it has this kind of apparently annoying negative sign. Okay, let's try to discuss what this expression is telling us. First of all, the risk premium depends on an external factor. The external factor is this expression here. This is something that is given by the characteristics of the fair game. Greater variability in the fair game, greater dispersion in the fair game, is something that you will perceive more negatively in terms of risk premium. The greater the variability of the shock, the more volatile the shock, the bigger the shock. So you tell me I can make 100 or lose 100, or I can lose 200,000 or make 200,000. That second game is worse to me because it has greater variability I will be more disliked, I will be more annoyed by that game, I will be willing to pay more in order to get rid of that game. The greater the variability, the greater the risk, the greater the risk premium for a risk adverse guy. Second thing, is something that I need to pay or what? The characteristic signs are positive and negative. So that denominator is positive, but that numerator is going to be negative if you are risk adverse. You have a concave function, like we are characterizing here, you are having a second derivative. So negative, negative, positive. Risk premium would be positive for a guy having a second derivative negative. So for a guy with a concave utility function, that risk premium is positive. That guy is willing to pay to avoid the risk. A risk neutral guy will be a guy for which the second derivative is zero. Risk neutral means linearity. A risk neutral guy will pay zero. Doesn't care about risk. And a risk loving guy, the first one is positive, that's common, but for a risk lover, the second derivative will be positive. Positive, positive, negative, the risk premium is negative for a risk loving agent. That guy is willing to pay to play in the game. The risk lover pays for taking risk. The risk adverse guy pays for avoiding the risk. Alright? The greater the variability, the greater the risk, the greater the amount you will be willing to pay. And then we observe something that does not depend on external characteristics. This is the characteristic of the fair game. The second thing is the characteristic of your personality. We have a ratio that depends on the curvature, so is second derivative. Second derivative captures the degree of curvature in the utility function. The greater the second derivative, the more concave the utility function looks like, the more risk adverse you are. So each of us will react in a different way to the same shock, depending on this shape of your utility function. So greater curvature means more risk premium. And the third thing that we observe is the dependence on your initial wealth. Whether you are poor or rich affects your perception of risk. The more wealth you have, what do you have? Poor and rich people. How they will perceive, who will be more willing to pay, who is going to be more willing to take on risk, poor or rich?
People, right?
Poor people, why?
Because they have like less to lose.
They have less to lose, and the marginal utility
Oh, it's bigger, clear.
is bigger. You see that? This U prime tells us how much utility gain we will experience by increasing your wealth. When wealth is small, when wealth is low, when you are right here at the beginning, the marginal utility is low, but the marginal utility is large. Because giving 100 euros to someone who is poor means a lot. So the marginal utility is going to be very high, and a very high denominator means a very small overall ratio. So the risk premium will be small for someone who has low wealth. For a poor guy, poor people are more willing to take on risk than rich people, paradoxically, because they have less to lose. You will say rich people have more, they can afford, yeah. But think, for instance, who plays with his life when he, for instance, tries to go from, North Africa, crossing the Mediterranean, or crossing the borders in Mexico to the US. Who are those guys like? Poor or rich? Who gambles with his own life in order to achieve something better? Desperate people. For those desperate people, for poor people, the perception of risk is not so aggressive as for rich people. Alright, guys?
I have a question.
Yeah.
So you said for the risk at first, the second derivative is negative and the seeking is positive, right?
The first one is going to be positive for everyone. The difference here is the second derivative. Negative for risk adverse, positive for risk receiver, 0 for risk neutral. Alright? So all of us have positive first order derivative, but the differences come from this risk perception that has to do with the concavity or convexity of the function. Question, guys?
I have another question here on this. Yeah, so what do you have utility up there? Yeah, to the right, right here. What about the second derivative?
Oh, I miss it, I don't need it. This is intentional. Why first order derivative or not? I'm perfectly happy now by having here this spin arrow. Because we want to solve for this spin. So that's why I put it a second order derivative, a second order expansion for this term, but just a first order expansion for the risk spin.
Oh,
Because
okay.
if I go in the second order, then I get a polynomial equation, and that makes things complicated. So because we want to solve for the risk premium, I go first order expansion. And we call this thing, when you use the first order expansion, we call it linearizing. I linearize utility function.
So only,
Okay? So just one final comment, guys. The volatility here, the sigma, will feel like risk. It's risk in this particular example. But we may wrongly conclude that variance is the measure of risk. It is risk in this particular example because more volatility in the fair game means more volatility in wealth, hence more volatility in utility. What people dislike is volatility in the utility function. Volatility, you are in macro, you will say what people dislike is volatility in consumption. That's what we dislike. Now, in generally speaking, volatility in returns is bad when the first order approximation, as I said before, this literature has been evolved over the years. The first approximation was insurance world. And in the insurance world, this example, more volatility, more variance in the fair gains means more risk because wealth is so proportionally to that scale factor. There is a perfect correlation between the source of uncertainty, which is the shock, and what happens to my wealth. But in real life, we know after these 50 years, there is not variance what necessarily matters to us. What matters is the risk that we cannot diversify intuitively. Even though variability is bad, we can remove in certain investments, in the stock market investments, we can remove a part of the total variability. So in the investment of stock markets, it's not the variance what matters, but covariance with risk factors. The sort of risk that you cannot remove, the sort of risk that remains, what we call systematic risk. Variance is a measure of total variability in my wealth. In this example, I'm perfectly okay because there is a perfect correlation. You talk about covariance, correlations. Well, that shock is bringing variance in that shock is causing perfectly correlated to my wealth. So I take it as a proper measure of risk. But in more general terms, we have other measures of risk which are more appropriate than pure variance. Variance is total risk. Total risk is not what matters. It's covariance. If you move that much, how much I move? A part of the total risk could be removed, and this is what happens through diversification. So it's not total volatility what will be discussed as the proper measure of risk in the second chapter, but things that have to do with the covariance, like a betas. Okay? In this example, which is taken from the literature, in the early literature in finance, and it's perfect, the remark that I want to say is that we may imply that variance is the measure of risk, only because it's in this example, it is. Here, it's perfect. But broadly speaking, variance is not necessarily what matters to us. It's a covariance what matters, okay? Just that remark. And like I said, guys, Are people risk-averse is wrong to assume that everyone feels the same thing? Yeah, different people may have different shapes of the utility functions. Even if we all are risk-averse, some of us may be more risk-averse than the others, and that's captured by this measure. Here we say there is something which is external, something that is internal. Given this metric, we define something that we call the coefficient of absolute risk aversion minus the second derivative evaluated at wealth over the first derivative for the utility function evaluated at wealth. This is an internal factor specific to each individual that characterizes your degree of aversion to risk. This is called the absolute risk aversion coefficient. And everyone has a different factor. So for instance, if we consider the most common utility function in macroeconomics, which is this, what is called the constant relative risk aversion, we have a function that depends on a coefficient gamma, which is like that. And for different values of this coefficient gamma, we have different shapes, all of them concave, but you will see that there are different degrees of risk aversion. The greater the second derivative, the greater the concavity of the function. This guy, for instance, that has a coefficient gamma which is equal to 1, is more risk adverse than that guy here. And this guy is less risk adverse than this guy down here. So this gamma coefficient in this particular utility function allow us to characterize different degrees of risk aversion. The literature says that we have a utility function that can be described in these terms with a coefficient gamma, which may vary from one individual to another, but broadly speaking, we have a gamma coefficient which is around 2. For gamma equal to 1, the utility function is the logarithmic function, like I showed Jim before, but we would say more representatively, most people seem to have a utility function which is described according to this utility function, depending on a coefficient in a coefficient gamma, which equals 2. So it's something like the green line versus the blue line, which would be the logarithmic function. And this is pretty much what we behave. But now, that means that all of us behave like that? No, there are risk-averse people and there are conservative people. So let me just show you a picture of what I'm saying. One of these two people is risk-averse, the other is risk-loving. Let me see if it goes through. Yeah. Now, yes, the two people, same situation. One is willing to pay for avoiding the risk. One will be willing to pay for taking the risk. Guess who is who? You're going to be identified with one of the two. All of you are going to feel more sympathy for one of them. One of you are going to be, I'm more like that guy, I'm more like that girl. It's like a beautiful, right? It's like, you feel like a bad for the poor guy, right? I'm like the guy. My wife is like the girl. She's not screaming, she's laughing at me. Like and he's like with this voice. Like that. I kill you. Super disadvantage. But some people are more. How many of you feel more kind of like a girl? We be more like she. 100%. How many of you look like the guy? I will be more like that. Like, no, I don't feel like that going to the. And my children are, oh, come on, Daddy, let's go. And my children is, Daddy, I'm gonna go there. We went to Disney. That's free. And they were, Daddy, do you really think you're gonna there and I'm gonna there, but you don't want to? And they were like, okay, I'm going there. And it's like, oh man, I'm gonna get that. And we all are like that. So it's not like everyone needs to be risk-averse or everyone needs to be conservative. It's just like that. But on average, there are what we say is most people that invest in stock markets, that make investments, behave like this guy. So when you put together people like the girl and people like the guy, on average, the pattern that emerges is risk-averse. So most people must be risk-averse. Even though there are people like this, we are not against that. It's just that on average, the market, and the student, what we call in economics, the representative guy looks like risk-averse. So we will demand a risk premium, etc. Okay, guys, time's up. Next week you have Nobel. You change me for a Nobel Prize, which is more than a fair change. I would say no complaint on my side. We will see us on Friday, and then we have Tuesday. We will have the second class schedule. So next class is going to be Friday. I think 3:30.
Yes.
3:30, right? You tell me what about the Stiglitz? Well, this is a super. It's a rock star. You can tell me, man, it's a privilege to see this guy. I was talking to another professor from philosophy. He said it's coming to Pamplona, which is kind of medium-sized city. It's not even Madrid or Barcelona, and still is coming here. It's kind of fall.
The probability, zero.
Not zero. It's coming on man. You will tell me. Have pictures with the Nobel Prize, it's like Engel. I remember first time I met my first Nobel Prize was Engel in financial econometrics, and I was like, I was completely shocked, and I was sat next to him because a friend of mine was organizing this conference, and he was the keynote speaker, and because he was saying, you sit there, and I sat there, and then comes Engel, and I was like, oh my God. I was, a young PhD student, I was like, I don't want to know, and he said, I was super rude, it's like a Spanish way of being, plus stress, plus English shock, and he was like, would you like to try that? I was like, no. And everyone looked at me like, oh my God, it's so real. But he was like, no, what I mean is, no, I'm so scared, I don't want to be here anymore. Take the chance, guys. This is something that must happen every day. By the way, the Nobel Prize were given last day, yesterday, you saw that finally.
Yes.
Surprise?
Yes, surprise. Honestamente. I thought they were going to address something more. I don't want to say important, but like urgent. Urgent. No, urgent. It's like we've experienced sustained growth, and I was like, which side of the world?
Sometimes they